In this presentation, we will aim to analyze the construction and working of linear direct drive motors, including detailing their many different types and classifications. The main topics that we'll attempt to go through are an introduction, an answer to why should we use linear motors, the two main types of motor drive systems, the linear induction motor and the linear synchronous motor, what are the different types of motor orientation, and finally, their applications in real-world scenarios. Linear motors are basically just a normal electric motor which has been rolled out such that the circular device that we're all very familiar with now appears to be planar. This means that instead of generating a torque like conventional electric motors, linear motors produce a linear force along the length of the device. This is exactly why we call linear motors direct drives and conventional motors indirect drives, as some sort of rotation to translation mechanism is usually required to be used alongside conventional motors. In the diagram figure 1, you can see a visual representation of a rotary or a conventional motor being converted into a linear motor. Why do we need or why do we use linear motor? The advantage of linear motors is obvious. The first, of course, is that we remove the middleman, so to speak. We do not need to employ a rotation to translation mechanism. And then, of course, there is the fact that linear motors minimize undesirable factors such as friction, heat loss, and etc. Another factor is that the removal of mechanical transmission components also removes backlash, which means that the response of linear motors can be many magnitudes faster than conventional motors, and we will see some example to that analysis later in this presentation. The linear induction motors are known for allowing high acceleration and deceleration, and they're also much better at driving vehicles up sharper inclines. This is again largely possible due to due to linear motors not using wheels and depending on frictions like a conventional drive system. The main types of motor drive systems are the high acceleration motors and the low acceleration motors. The most popular variety of the linear motor under high acceleration motors is the linear induction motor, or LIM, and the most popular form of motor being used under low acceleration motors is the linear synchronous motor, or LSM. The linear induction motor. The AC linear induction motors are the most common form of high acceleration motors, and similar to their conventional counterparts, such motors consist of an active three-phase winding and a passive conductor or a plate separated by an air gap. These are often regarded as the backbone of the linear motor since they are the most widely used category. The three-phase winding is referred to as the primary part and the reaction plate is called the secondary. The magnetic flux develops in the primary and eddy currents are induced in the secondary. The magnetic flux and the induced currents then interact to produce a linear force. Note that the eddy currents basically produce their own magnetic field, which is opposed to the original field in accordance to Lenz's law. The repulsion between the two fields provides the translational force, that is a linear force, which drives the motor. Either the primary or the secondary may move depending on which is fixed and which is left free to move. The synchronous speed of the magnetic field is given by the formula where F subscript S is the supply frequency and P is the number of poles. The second formula gives the velocity of the traveling field pattern where T is the pole pitch, also defined as the distance between two adjacent poles. The speed of the secondary in the linear induction motor is given by the third formula, and note here that S stands for the slip of the linear induction motor. The two different types of constructions of the linear induction motors are the single-sided LIM, with a single primary and single secondary, which we have been seeing so far, and the more unique, the double-sided LIM with true primary and a single secondary. This allows for more effective utilization of the flux being generated from both sides. And now let's talk about the factors affecting the performance of an LIM. The first is obviously the thrust, which refers simply to the driving force producing translation in a linear motor. Usually a higher magnitude is desirable. The figure on the right shows the behavior of a standard LIM with a pole pitch of 5.6 cm, which has a thrust proportional to the square of the applied voltage. This in turn reduces as the slip is reduced and is analogous to an induction motor with a high rotor resistance. The second factor is the end effect, which refers to the phenomena whereby magnetic energy is lost at the end of the primary by the relative movement of the primary and the secondary. It is undesirable and causes loss in performance and efficiency. The third factor is the levitation, which refers to the presence of an air gap due to an electrodynamic levitation force. This occurs in single-sided motors and does not occur when an iron-backed plate is used as the secondary, since the resultant attraction overwhelms the lifting force. The fourth factor is an air gap between the primary and secondary. A large air gap can serve to reduce the efficiency of the motor, since it decreases the force produced for a given power input. A larger air gap also increases the inductance of the motor, which means that we have to spend more on purchasing and installing the necessary capacitors. The figure on the right shows the effect of an air gap width on thrust and line current, as well as the optimal air gap value, which is found at the intersection of the current and thrust curves. An optimal air gap length needs to be maintained for maximum performance, and the mean value for the air gap standard in industry is 2 mm with a variation of 20% acceptable. Now let's talk about the linear synchronous motor, which comes under the low acceleration motors. This consists of an active winding and an array of alternate pole magnets which are separated by an air gap. The magnets may be electromagnets, permanent magnets, or even superconducting magnets. The coil assembly is generally called the primary part, and the magnet assembly is called the secondary part. You can see a representation on the image at the bottom of the slide. About the different types of construction of the linear synchronous motor. The flat linear motors basically have a single magnetic track as opposed to their U-shaped counterparts, which have a second magnet track such that the moving part moves between them. Flat motors usually have a higher flux leakage. As the name suggests, an iron core motor is simply the one in which the coils are wound around iron laminations. This has the advantage of reducing flux leakage, maximizing flux density, and output force. Now let's talk about the factors affecting the performance of an LSM. The first is the flux density, which is the magnitude of the magnetic field generated. A high flux density corresponds to a higher driving force. The second factor, the flux leakage, is the flux that is lost to the surroundings. Low flux leakage corresponds to higher electrical efficiency of the motor. The third, the moving mass, refers to the moving components of the motor, and lower mass is preferable in most cases to produce a higher acceleration. The fourth, the cogging force or detent force, is present in a linear motor due to the presence of iron and is basically the attraction of iron to any permanent magnets in the motor, resulting in a cyclical force, ripple over the travel distance. It's undesirable and reduces efficiency. Now let's talk about the two main types of motor orientation. Consider the motor orientations explained from the perspective of a magnetic transportation system where a vehicle has to move along a guideway. The short stator motor is the motor where the stator is the shorter than the rotor because it is on the vehicle and the reaction plate is located on the guideway. The power source must be on the vehicle, and we might even have to perform cable management, which is a separate problem. The long stator motor is when the stator is on the guideway and must be energized from a power supply as suitable, while the vehicle has no such requirements, consisting only of the reaction plate or the magnetic array. The applications of the linear motors are numerous. In transport, for example, they're mainly known for the maglev propulsion and high-speed train networks, for shuttle propulsion, for example, by NASA, and even for launching aircrafts. And then, apart from their transportation applications, the vertical linear induction motors are known for being used as lifting mechanisms in mining. Linear motors are also used as sliding doors in liquid metal pumps and for metallic conveyor belts. These are a list of the references that were used to compile this presentation. Thank you for watching.